Greetings everyone. Today we're going to be talking about entropy. In this figure what we have is a bunch of ink that's been deposited onto the surface of water. So the ink, which was initially high concentration up here, so we could do like C, high, and down here the concentration of the ink is really low. What we would expect is that everything is going to get smoothed out. So eventually the ink is going to be evenly spread throughout the whole volume of this water. And the reason why that is because of how entropy is going to evolve in the system as it reaches equilibrium. So this is a lot of key words: entropy, equilibrium, diffuse, and we're going to talk about all these and how it pertains to statistical mechanics. First, let's look back at random walks. This is basically our simplest model that we could have of maybe how an air molecule bounces around this room. And you could follow how the air is, and maybe it looks like it's going to be in this region for a little while, and then this region for a little while, and this region for a little while. So there's two things that I'd like you to see in this picture. One is that, okay, it follows and it looks like it's in some region for some period of time before it moves somewhere else. The other is that there's basically no structure beyond that. So it's not going to just move in some straight line. It's not going to move in a circle or anything ordered like this. But what we do see is that there is these big patches where it looks like it's spending a lot of time in. And then if we zoom in, we can find there's a smaller patch where it spends a smaller amount of time. And if we zoom in again, there's an even smaller patch where it was again and again. And that is that there's different length scales. So here's a big length scale, here's a smaller length scale, here's an even smaller length scale. And this is part of the fractal nature that we observe in random walks. So another occurrence in the world is in the stock market. And of course we couldn't predict what's going to happen the very next day to this stock right here. But what we could do is talk about how an ensemble of stocks are going to behave. We could also look at how proteins fold, or how bacteria move from one location to another, or even how ions have facilitated diffusion across a cell boundary or interact with a protein. So these are all real-world models of random walks, and we're going to talk a bit more about their behavior. So again, if we look at just one random walk, we couldn't predict which way it's going to step in the very next one. Is it going to go to the right? Is it going to go to the left? We don't know about that. But what we can do is we can look at a whole ensemble of these random walkers, not just one air molecule in the room, but we can look at all of the air molecules in the room. We can say, how far on average do we expect things to move? And you would be right into saying that on average, it's not going to move. Basically, if the whole system isn't moving to the right and things have an equal probability of moving to the right and to the left, after n steps, we're still going to be right back where we started, on average, for a whole system of walkers. But what may be more useful to think about is not how the position evolves over time, but how the variance of these positions evolve through time. And this is not going to be zero. So this looks at the variance where each of these walkers might end up being at some point in time. And so this is, it can be written this way, it can be written sigma squared. You might even hear of something called mean squared displacement. And that would be the same kind of idea as this variance. And what's interesting about this is that it's not equal to zero, and it's basically going to increase linearly with time. And this is actually really fascinating, is why it is linear. If we look at just a single particle and it moves with some velocity v, we would expect its position to move as vt. So then we would expect the mean squared displacement of a single particle that's not interacting with anything else to go as v squared t squared. So this is the real key part here, is that this squared here. This power of 2 tells us that the behavior of this system is ballistic, so basically nothing is interacting with anything else. But if we look at some system and we measure this mean square displacement or this variance, how it's evolving with time, and we see that it's a line here, this tells us that diffusion is dominating this system. This is the kind of behavior that we have. So this equation is called the Stokes-Einstein equation, and this is actually what Einstein worked on for his PhD thesis. So let's look a little bit more at what's happening in each of these three circumstances, and we'll relate this back to what we would expect from random walk. So here we have a bunch of particles on one side of the room, and you can imagine that this is maybe our ink or something like this that's been deposited at the top of the container. And you could say, what would you expect to happen as we let the system evolve in time? And you would be right into saying that we would expect this to happen. We would expect a high concentration to be smeared out evenly over time. We could also look at, maybe we put a bunch of green particles over here and a bunch of red particles over here. What do we expect to happen with time? Again, we expect that over time the system is going to evolve into some state where green and red are living harmoniously together, so everything is nice and smeared out again. What if we put two different systems that were at two different temperatures together? What would we expect? So again, you'd be right in thinking that eventually the temperature is going to be the same everywhere. This could be like a frying pan, a cold frying pan on a hot stove element. Eventually, you hope that your frying pan is going to be the same temperature as the stove, so you can cook something. So in each of these cases, what we see is that everything is getting smeared out. So this smearing, we can think of more quantitatively in terms of diffusion. So here we had a bunch of stuff on one side, everything gets smeared out. The reason why is because the system is evolving like a random walk. Eventually, everything is going to be nice and diffused. And we can also talk about this in terms of entropy. But to do this a little bit more, we need to talk about what entropy is and what it isn't. So if we look at this state right here, it looks very ordered, like a checkerboard. And one thing that would be easy to do is that if we looked at some crystal, maybe this is a sodium and this is a chlorine ion, and they alternate like this crystal lattice. If we know just a very little amount of this crystal, just this 16, and we can see that sodium and chlorine ions, alternate throughout this crystal. We can just look at a small subset of this, and then we can predict what's going to be throughout the rest of this crystal. But if we have a system that is not so ordered and crystalline, maybe we have a glass that looks like this and things are a bit more disordered, then we would not be able to predict, this element over here, is this going to be a sodium or a chlorine ion? We don't know. Based on what we've seen over here, like we would for this crystal. So, two things here. One is that we can't make these predictions because there's this disorder that's in the system. This is related to information and how information relates to entropy. And another is that if we swap some of these tiles around, would this state be discernible from the previous state? And if the system is disordered, you would not be able to tell the difference very easily. But if we swap these two, and now this guy is white and this guy is red, we would easily be able to say, hey, this crystal has a defect right here. So how can we calculate entropy? Basically, we need to know two things. One is that entropy is extensive. So this means that if we have one system A and another system B, and we put these guys together, entropy of both of these systems together, we just add things together. And this makes sense because if we look at two dice rolls, we know that for one state we have 6 rolls, and for another state we have another 6 rolls. So this means that our total number of states is 36. So you could say, well, our entropy is additive here, but this is a multiply. But entropy is calculated using the logarithm of the number of states. So actually these right here, these 6, are are omega A and omega B. So when we multiply these guys together, and we can take the logarithm, so we can say log of 6 times 6 is going to be equal to the log of 6 squared, which is the same as the rule of logs is that you can bring this 2 over here, and now 2 log of 6, which is the same thing as saying log of 6 plus the log of 6. So here we have entropy of 1 plus the entropy of the other guy that we have. So entropy is related to the number of the ways that the system can rearrange itself without affecting this macrostate. So it basically means that all of these guys are the number of our microstates. We're not going to worry too much about this K right here for right now, but this is the Boltzmann's constant. So basically if we have a system, then we would expect that the entropy of that system is never going to decrease if the system is isolated. But what could happen is that this system will go towards equilibrium, and what we mean by that is that if we look at the entropy versus time, is that the entropy of the state could go like this, whereas this value right here is our maximum entropy state. We could start off with a bunch of gas molecules that look like this, and what we would expect to happen over time is we would expect the system to evolve to a state like this, where the system is much more disordered. So how does entropy relate to energy? Well, if we go back to our hypothesis that energy and volume are all under this equipartition, which means that everything is split up evenly among all the particles, then the total amount of thermal energy is, on average, we just divide by n, so we can get the average kinetic energy for one particle. Alright, so then this is also divided up among all the degrees of freedom that a particle has. So if you look at a particle in 3 dimensions, we got x, y, and z, x, y, and z. And then now you can look at the velocity vector of that guy, and it's got some velocity in x, some velocity in y, some velocity in z. We would expect that on average, not all the time for every particle, but on average, if you looked at a particle, that x, y, and z are all going to have the same amount of energy. So that means that they all have the same amount of v squared. So then we can look at this 3/2 mv squared for just one element, or this VRMS. This RMS means root mean squared. And we can also look back at this definition and put these two guys together and get VRMS is equal to 2 times this thermal energy per particle, right? Well, total. And then we divide by n, so this is the per particle part. And then divide by m, because we have an m here. So this is our VRMS. This is how fast we expect a particle to move in the gas on average. And if we want to relate this to something that we can measure, we can't measure E-thermal very easily. What we can do is we can measure temperature very easily. And so the thermal energy that is in a system is going to be this 3/2. This 3, again, is this degrees of freedom. So for a monatomic gas, the only degrees of freedom that we have are x, y, and z that the velocity vector can be in. And then kt. And so we can plug this into this E thermal and get that VRMS is equal to 3 kV. kV again is this Boltzmann's constant. And then T, and then divided by an individual particle's mass. So this is just one particle mass. Let's look at some problems. So here we have a system with a bunch of particles, n number of particles. We would like to know how many basic states are in this system. So here we have 10 particles in a system that has 100 different compartments. Alright, so that means that for one particle, there's 100 different places I could stick that particle. But now I have 10 particles, so that means that I'm going to take this number of states for one particle and I raise it to the n. So this is the m to the n, and this is going to be my number of states, my omega. Okay, omega looks more like this. It's going to be 10 to the 10. And this is a huge number. This is like 2 to the 20. So this is, 10 to the 20. That would be a lot of zeros to write down. But what is the natural logarithm of this number? So we can do log of omega is going to be equal to the natural log of 10 to the 20, which is going to be 20 times the natural log of 10. And now natural log of 10, that's easy to compute. And then we just multiply that guy by 20, and so we're going to get 46. This is a much easier number to work with than this 10 to the 20. But now let's put this into practice, our new definition of the number of microstates. So we have two boxes. Each box has the same volume. Box A has a bunch of helium atoms, and box B has a bunch of argon. Alright, you guys are argon now. And so we have these two boxes, they're separated, and now we're going to say, we're going to pull these partitions up, and we're going to let the system evolve towards equilibrium. And so what we would expect is that argon, half of these argon are going to move over here, and half of these helium are going to move over here, and the system will be in nice, happy equilibrium. So what is the entropy change as we evolve from the state towards equilibrium? So what we need to do is we need to calculate the number of states that helium can have, and we need to calculate the number of microstates that our argon can have. And so when we plug this in, we need to do the number of states. So the state of helium could be on the left or on the right. So that's 2 states, and we have 2,000 of these guys. And then for argon, we have 2 states, but now we have 3,000 particles. So if we want to calculate the entropy, we're going to take the logarithm of these 2 states. And so that's 2 to the 2,000 plus the logarithm of 2 to the 3,000. And so then that means our entropy is 2,000 times the log of 2 plus 3,000 times the log of 2. So this is equal to 2,000 plus 3,000, so that's 5,000 times the log of 2. And there's our entropy. So for our final problem, we're going to be looking at a sample of neon gas. This neon gas contains 1 mole, which is the 6.02 times 10 to the 23. It's at standard pressure, so 1 atmosphere, which is 10 to the 5th Pascal. And we're also at standard volume, so this is our 1 liter of gas, so 22.4 times 10 to the minus 3 cubic meters. And then we also are given M, which is a 6.409 times 10 to the minus 26 kilograms. Now we want to know what is the speed of a neon on average. So we look at the kinetic energy, and we get 3/2 in kBT. So for one, this 3 right here is because we're a monoatomic gas. And that's important because monatomic gases are ideal gases, or very close to ideal gases. And then this is for our 3 degrees of freedom, so X, Y, and Z. So basically we can ignore vibrational and rotational degrees of freedom that you would have with like oxygen or something. So this kinetic energy is related to 1/2 mVRMS squared. And so then our VRMS is going to be equal to 3 kBT all over m. And we're going to take the square root of that. So now we just plug in all that we want to know. So this VRMS is going to be equal to 3 times this 1.01. Basically, we need to find a way to get T. So T, if we look at an ideal gas, we get PV equals nRT. But R is this ideal gas constant. And this is really NKT. These are both the same relationship here, but we're replacing one constant, this R, with K. And the difference between these two is this guy is the number of moles, and then this guy is the number of atoms or molecules. And then this is Boltzmann's constant here, this K. So we can replace one of these two, and what we need to do is solve for T. So that means our T is equal to PV over NK. So here we have 3 times kBT. So we're going to have 1 K up here on the top. I'll get to that in a second. Times 10 to the 5th Pascal times kB. And then now divided by N. So N is the number of molecules. So 6.02 times 10 to the 23. And then now times another K. But that's convenient that these two guys cancel off. And then now I need to divide by M. So M is a 6.4 times 10 to the minus 26. And then I can't forget to take the square root of this guy. So then my VRMS, if you forget to take the square root, you're going to get a very large number. So my VRMS is going to be about 419 meters per second.